Go. All right. Hey, everyone. Welcome back. Today we're going to do RNNs and LSTMs, and I'll pass it over to Naveed, who can explain what that is.
Yeah, so previously we covered CNNs, which were uh, mainly useful for imagery data because of the special filters that we used in order to extract features from the images. The idea with RNNs is somewhat similar, only that this time the information that would be available would be distributed across time. So for spatial distribution of features, we use that filter, which we kind of scanned the image through that filter, and that filter extracted whatever feature that it was looking for. And the good thing was that the filter was tunable. We didn't set the feature that it should be looking for; rather, training did the magic. And exactly similar strategy would be utilized in order to extract information that is distributed across time. So let's first see why a simple neural network wouldn't be able to uh, do that job of extracting features from time. So sequential data appears in like lots of different scenarios. You can have like the textual data is sequential. Words follow each other in a special manner. Um, but it's not just textual data. Sequential data could be found in, let's say, uh, in forecasting, kind of like forecasting data is also sequential data, and you can think of lots of other different examples where not just only the features, the exact values are important, but how they occur, how they appear in time is also important. Particularly, I'll be explaining the RNNs in the context of forecasting because James is going to show you the example that he's going to show you would be one of forecasting. So that's why I'll also try to restrict the discussion towards that. But just keep in mind that the same principle is used if you are doing, let's say, textual analysis, text related stuff, or any other domain where the data could be treated as a time series data. So, suppose we have a pattern, values are occurring in this manner. So, x1, x2, dot, 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 x, tx. Now, this superscript that I'm writing here represents the position in time. So it's not like this is one example and this is second example and this is the third example. This is different time steps. So this is the first time step, this is the second one, and so on. Let's say for now we have restricted our discussion that the total length of these samples is tx. So tx is nothing but simply the total length of the pet of the sequence that we are looking into.
So,
So if
is it important that these are evenly spaced samples in time?
evenly spaced. Now that is, I mean, it's not important from looking from the algorithm point of view. It could be important from your own understanding. Like if then the model is predicting future values,
Hmm.
you should then know that what those values mean. Are they evenly spaced or are they repeating themselves after varying lengths? So the model is going to treat all of them just as a sequence of values, and whatever it is predicting then is also going to be of that same variation. Like if x1 and x2 are greater, the duration is greater than between x2 and x3, let's say, the model, the prediction that you get from the model should also be in that pattern. But it doesn't matter to the model what duration is between each value. So that's for our own uh, analysis, maybe. Does it make sense?
Yeah. that makes sense.
Okay. So let's see. Just like I said, if you take a normal neural network and try to feed these values through that, um, it will treat every value independently. So it won't. It would take into account what this particular value is, but it won't take into account that x1 here is occurring or is preceding x2 and x2 is preceding x3. In other words, if you even shuffle the space of these values, the neural network is unable to determine the difference between those two different patterns, for the simple reason that it is only taking into account individual values and not the sequence which they are occurring in. Does this make sense?
Hmm.
So this is the principal reason why we cannot make use of the simple fully connected layer. But apart from this, there are other reasons as well. Sometimes when you are dealing with sequential data, suppose if we are, let's say, uh, experimenting with textual data, sentences can occur, can be of different lengths. So if you would be feeding this data through a normal fully connected layer, it requires every single example to be of the same length. So let's say this is the first training example. It would require the second training example to be also the same tx length. Um, and if it is of a different length, then the network is going to throw an error saying that every example is not of the same length. Now you can work around through that problem by, let's say, pairing the sequences. So you can add zeros if it is shorter than the first sentence, or you can also truncate it if it is, let's say, longer than that. But that doesn't seem like a good strategy, because if you are pairing it with zeros, you are redundantly adding some values, and if you are truncating it, you are losing some information. So even though you can work around, technically work around that problem, but still it's not a good or efficient thing to do. So these two reasons kind of serve as the motivation for why we would need a different model than what a simple fully connected layer is doing. But the principle or the main motivation behind it is we need to take into account the timing information that is distributed across these samples and not just only the features themselves. So let's see um, how does a recurrent architecture takes care of this problem. So let's say we have a simple neural network, a fully connected layer. I'm just simply reconstructing it like this, but you can consider this as a simple NN architecture or fully connected layer. And let's say I want to feed this data, which is occurring sequentially through this network. How does it? How does the information or the data flows through this network? What happens is you take the first value, which is x1, and you feed that through the network. And then uh, before you feed the second value through this network, you not only take the second value, but you also take the what is called a feedback or a recurrent connection from the previous input that you have fed through the network. So you take a feedback um, connection from the previous output as well before you feed the the new sample. Just a second.
Hmm.
Okay, so there's a previous output. There's a connection from the previous input, and then there's this second input that is coming, and we feed that through the same network. Now I'm drawing this structure again, but this is not like a different network. This is the same network. I'm just unrolling it through time, if you call it that. So this is the same architecture, but now when I feed it the second sample or the second feature from my same data, alongside it, there's what is called a feedback from the previous input as well. So let's call it A1. and that goes through this network again. And then when I try to feed the third feature, let's say X3, I take the same architecture again, and alongside the third feature, I also take an output from the previous input as well. So let's call it A2 this time. And this may be called as A0. So initially, this is just, you can initialize it to be anything. It could be all zeros because we don't have any previous input. That's why you can, this first feedback could be just simply all zeros. But when the first feature comes, you feed it through the network. There's a feedback. There's some output from that, which we feed alongside the next feature, and then there's an output from that one, and then we feed it with the third input, and so on. Let's say the total length of it was xtx. So you can take the xtx example and feed it to the same network, and there would be feedback coming from the, let's say, atx minus 1, which just simply means the last input. And then finally, you can generate an output. So let's call it y hat here. So if you see now, in order to, let's say, um, generate an output y hat, it is the information across that is distributed across time can also does contribute to the final output. So let's say if you want to find out how can this x1, or how is this x1 playing a part in producing an output, well, x1 comes here and then it travels across the network um, like this, and then it finally contributes its part towards an output. And same goes for x2 and for x3 and so on. Does this thing make sense?
Yes, it does.
Okay, now the key part here is that all of these different the timestamps that we are feeding through this network, all of them are associated with this network through the same set of weights. So let's call these weights as WAX, which just simply means the weights associated with the input that is coming from the data. So this set of weights is the same across all the network. So it's not like every time I'm feeding a different time step, I am associating it with the different words. The same set of words just simply means that this is the same architecture. It's just that we are now feeding the features one at a time. So this is first input coming, and then sequentially we feed it the second input, and then the third input, and so on. And all of them are fed to this model using the same set of weights. And similarly, the set of weights associated with these feedback connections are also stays the same across the network. So this A0, which could be all zeros, are associated with, let's say, set of weights WAA. And those WAA weights stays the same across the network. So um, in order to generate um, this A1 or this A2 or this ATX minus 1, the set of weights associated with it are all the same. And then the set of weights associated with producing an output is also stays the same. Now, for this particular example, just like I said, we are going to be demonstrating the example through forecasting. So in forecasting, we are just simply taking the previous n steps to produce the next value in the sequence. That's why we are just only having a single output by the end of it. But for different examples, let's say if you would be using this network for, let's say, language translation, maybe you would be required to produce an output at every single step. So if you feed a word, you might want this network to produce an output. And to feed two words, or like the sentences gradually increasing in length, you would be on the fly translating that portion, whichever is coming from the input. So in that case, you would be producing an output at every single step. But for this example, we're not doing that. So that's why we only have an output which occurs at the end of the entire sequence that we are feeding to this network. And that, to generate that output, you can the set of weights associated with it could be called, let's say, WYA. So as you can see, we have three different set of weights associated with this network. One is this WX, which is responsible for processing the input. One is WA, which is responsible for generating this feedback connection. And one is WYA, which is associated with producing an output. Now, let's see how the outputs mathematically, or let's see the equations for the forward propagation to this network. So in order to generate this A0 or this AT, which the T literally depends on which step you are talking about. So in order to generate that, AT is nothing but G1, where G1 is just simply the activation function, WAA times A T minus 1 plus WAX XT plus BA, which is the bias term. And then to generate the output, Y hat T, where this T here is just 1 because we're producing a single input, but this could be, just like I explained, you could be generating an output at every single step as well. So that's why there's a T here, WYA AT plus the bias term BY. So let's see what's happening here. In order to produce this feedback connection, which we are feeding with the next input, it is taking into account the previous connection that is coming. So this is represented with this AT minus 1. We take the previous connection multiplied with this set of weights, which is WAA, and then we take the current input, which is this X represented by X. So XT represents the current input. In order to feed this to the network, we multiply it with this set of weights, WAX, and then there's just the bias term, which this bias term is associated with this feedback connection. And then in order to generate an output, we just simply take the set of weights associated with the output, and we are only taking into account this AT, which is this feedback connection coming from the previous layer, and then adding to it the bias term associated with the output, and that's how we generate an output. And this is literally the forward propagation step through an RNN. Any questions?
We've, I don't know if it's a dumb question or not, but for the first step, like the first propagation, we don't have the previous term, right? We don't have AT
Exactly.
minus 1. So what would we be using in that case?
In that case, you can just simply initialize them to be all zeros, or it could be any other random initialization. So you can just like for simple neural network, when initially you initialize the set of weights to any random values. So this could be any random values. Usually these are all zeros.
Cool.
Vector, do you have any questions? Now this representation that I have drawn here, this is usually the unrolled representation. So I'm just simply taking the same architecture and unrolling it through time. That's why you see these different network drawn over and over again. But usually, if you read through a deep learning book or any machine learning book, this recurrent architectures are usually drawn like this. So you have this network, and then there's an input to it, which is represented with xt, t for the time step, is WAX, which is the set of weights associated with it, and then to demonstrate that feedback connection that is drawn usually like this, and the set of weights associated with it are WAA, and then you can generate an output from it, Y hat T, which are associated by the set of weights WYA. So this is usually the diagram, the concise diagram that you see drawn in in textbooks. But the idea stays the same. This unrolled diagram usually it's easier to understand what's happening to this network. And there's also, in order to demonstrate how a single RNN cell or a single RNN neuron work is usually also demonstrated through this diagram. So you have this RNN, single RNN cell or neuron, whatever you may call it. We have this previous input, this feedback connection coming from the previous input, AT minus 1, that comes through this network. Um, there is this you can call G1, which is the what is called the nonlinear activation function, and then we have the input xt coming through it, and then both of these two are used to generate the next feedback step. Usually, it's called a hidden state in a recurrent neural network terminologies. But I prefer calling it feedback just to demonstrate what it is doing. And then you can generate an output through, let's say, G2, which is a second activation function, Y height. So this is usually, this diagram is also common if you read through different blogs explaining RNA architectures, or maybe sometimes it's also drawn in
So that's the
text.
same. So that's the exact same thing as the equations that you just wrote, right? Just in a.
This is exactly, this is exactly the same thing that these equations, which I demonstrate through these equations. So
Yep.
if equations are easy for you to understand, you can literally stick with the equations. But if you are a more visual person, you can also understand it through this diagram. But this is the simple RNN architecture, simple recurrent neural network. Now, things don't stay here. There are a lot of more variations performed on these recurrent architectures in order to make them even more powerful. And in a while, I'll show you an even more a scary diagram where there are lots of connections and stuff. But first, let's just quickly talk about how would you implement gradient descent through such a network, or how would you train such a network through, let's say, backpropagation. So you saw the forward pass, and let's just conceptually understand how could you be implementing, first computing the gradients of this network, and then making use of those gradients in the gradient descent algorithm to update the weights. So suppose I'm interested in, let's say, figuring out the derivative or the gradient of the loss function with respect to some of the hidden weights. Let's say this WAA, or let's say with respect to WYA. How would I do that? So first, this network, let's say we are making use of it for forecasting. There would be a loss function which would be accumulating the differences between what this network is generating and what the true output is. So let's call that loss function is loss, which is nothing but the difference between the model prediction and the true output. Usually for forecasting, you make use of the same loss function as you use for regressions, which is mean squared error, or you can also make use of MAE, mean absolute error. But that's just a typical loss function that we've been using so far. And let's say I'm interested in finding out the derivative of the loss function with respect to, let's say, this WAA, which is the parameters associated with the feedback connection or the hidden state. So as you can see, we cannot directly compute the derivative of the loss function with respect to this, because the loss function is a function of what the model is producing and what the true output is. And then what the model is producing is internally a function of the hidden state, and then the hidden state is a function of WAA. So we would have to make use of the same chain rule of derivatives in order to reach to this WA parameters. So let's write that equation. So d loss over dWA would be nothing but the derivative of the loss function first with respect to dy height, and then that would be we would multiply it with the derivative of the model prediction with respect to the derivative of the AT. Now, the key thing to pay attention to here is this T term, because the hidden state is not just one. This is distributed across the different time steps of the input data. So this would be crucial. And then we take the derivative of the hidden state with respect to WAA. And that's how we can compute the derivative of the loss function with respect to the hidden parameters, the parameters associated with the hidden state. And once we compute the derivatives, we can then simply plug it inside the gradient descent equations in order to update those set of weights. So just like I said, the important thing here is this T term. This T varies. It starts from 1 and it goes up to Tx, because remember the total steps involved in the input sequence was Tx. So you would not just have to compute the derivative of the output with respect to one value of AT, but you'd rather accumulate those across the different time steps. And that's why this particular variation of the backpropagation is called backpropagation through time. So this backprop through time just simply means you are accumulating the gradients across the different time steps. And then you get the cumulative effect once you accumulate all those different gradients, sum them all together, and that would be the final derivative of the gradient that you're looking for. Does this make sense?
Roughly, yeah.
So
Yes,
the
it
idea here
does.
is just to kind of give you a rough idea of what's happening. Of course, the real working of like the detailed math of RNNs is quite complex. We wouldn't be able to discuss it through 1 hour session. But anyways, this is the overall kind of the broader picture of how an RNN could work. But there are certain problems with this kind of architecture. The principal problem with this kind of architecture is what is called the vanishing gradient problem. Now, what is vanishing gradient? Just like I explained that in order to produce an output, which is why I hate here, um, the the weights or the information flows through this network in this manner. So let's say if I want to find out how much x1 is contributing here, x1 starts from here and then it propagates across different time steps, and then it kind of accumulates across the different the contribution of every single step is kind of accumulating across time, and then finally they contribute their total sum in this final step. But the problem is if you make this sequence longer and longer, the information that is coming from the initial time steps, it would be more difficult for it to flow through the longer sequence. The longer this context length becomes, or the context window becomes, the difficult it is for the network to then remember what was occurring in the um, uh, initial steps of the sequence. And this kind of problem is usually called the vanishing gradient problem. So the vanishing gradient term just simply comes from the idea that if you keep computing the derivatives of the output with respect to every single time step, the derivatives are nothing but they keep getting smaller and smaller as you keep calculating the derivatives over and over again. So for shorter sequences, the values could still be out there, but the longer they becomes, the values tend to become smaller and smaller and smaller, and eventually they vanish to zero. and that's why this term vanishing gradient comes from. There's also an opposite term which is sometimes called, which also could sometimes occur, although that phenomenon is rare, but it's called exploding gradient. Sometimes what could happen is that the derivatives, while they accumulate through time, could become so bigger that the values are just simply enormous. And that problem is often called exploding gradient problem. Both of them are associated with the simple RNN architectures, but vanishing gradient occurs more than the exploding gradient. Now, in order to solve that problem, different variations of this RNN architecture were proposed. One of it is called the gated recurrent unit GRUs, which is somewhat recent. There was published, I think, in 2014 or 15. But there's a uh, more robust variant of it called the LSTM, or long short-term memory cells. Now, LSTM, although they were published earlier in 1997, but later on they were more successfully used for in multiple different domains. So they were used in the NLP in order to do language modeling, um, and they are still used for all sorts of different problems in for time series analysis, for forecasting and stuff. And particularly, that's what James would be showing uh, in the coding lessons. Let's quickly just go through what an LSTM cell does as compared to the simple architecture, the simple RNN cell. So if you go through the LSTM paper, the paper is it goes through lots of details of the vanishing and exploding gradient problem. We won't have time to, to cover it in such detail, but I have a simple picture of it, um, which is here. You see this picture?
Yeah.
Okay, so this is a single LSTM cell. They are, the LSTM solves the problem of vanishing gradient through what is called this gated architecture. So you have different gates. This blue dotted rectangle that you see, this is called the forget gate. And then we have this input gate, and then we have this output gate. And we also have what is called the cell state. Now, different in different places, people have like explained each of them according to your own examples. But what I preferred was maybe I would ask a simple explanation of ChatGPT. I'll quickly show you what each of those gates are doing. And then the usually the strategy that I apply while understanding these networks is first understand the technical implementation of them, and then you can literally tell whatever story to yourself which makes you sleep better at night into what it would be doing, and it won't matter because no one understands fully what they do. Anyways, so let's see. You see the screen, right? Oh,
It's back.
Yeah, no.
okay. Yeah, so we have these different gates. Let's see, what is forget get. What is it responsible for? So the forget get decides what information from the previous cell state should be discarded. So the previous cell state is nothing but that feedback connection which I was talking about. So I represented using AT, but here that is represented as HT. So this is the previous state coming as HT minus 1, and then the next step of it is called HT. So it says that the forget get is responsible for, or decides what information from the previous cell state should be discarded. It outputs value between 0 and 1 for each number in the cell state, where 1 means completely keep this and 0 means completely forget this. And it does it using the sigmoid activation function. So you see here a sigmoid activation where it would just squash the output between 0 and 1. So if it is 1, it just simply means completely keep this previous information. Or if it is 0, it means just throw away, because whatever is coming from the previous steps, we have already, like it has already played its part, and now we no longer need it in order to be passed through the next steps. So that's how it keeps a track of that. And then we have input get. So it determines what new information should be added to the cell state. So remember, this input get is associated with what is coming at the current time step, which is xt. So input get decides what new information should we add to the cell state. So what is cell state? We'll see that as well. But then we have the output get. So the output get controls what information from the cell state should be outputted as the hidden state for the next time step. It filters the cell state through a sigmoid function and then passes it through a tanh function to scale the output. So this output gate, which is represented here as this green box, determines what um, uh, what should be the value for this HT, or what information should we feed through should generate from the current step in order to be passed through the next time step. So that's what this output get is doing. And then on the top of it, you see this one long connection, which is called the cell state. So what is cell state responsible for? The cell state acts as the memory of the network, carrying information across time steps. The cell state is modified by the forget and input gates, and its filtered version is passed through the output gate. So this top connection that you see, this is where the term long is coming from in the LSTM, long short-term memory cell. So this cell state determines what information across all those different time steps should we be keeping, and what information from the earlier steps should be passed all the way across the last steps, and what should be maybe passed um, to the middle of the time steps, and so on. So this is responsible for that long-term memory of the network, and this connection, this HT here, is responsible for the short-term memory that might be useful in order for this network to produce an output. And these are its equations. How do we compute the forget get? We have a set of weights associated with it, represented by WF, and it takes input as the previous cell state in the current time step, and there's the bias term. How is this input get determined? It has its own set of weights represented by WI, and it takes the input from the previous cell state in the current time step. And then we have the output gate represented associated with a set of weights WO, and it also takes into account the previous cell state and the current time step, and the bias unit. And then we have the cell state, which is represented by this equation. This circle with a dot just simply says pointwise multiplication. And I mean, that's all I can currently say about this LSTM cell.
Yeah.
I would love to answer any questions.
Okay. So the input gate is basically the remember gate, right?
This input get is
Show
actually
the. Can you show
determining.
it again? Can you pull that up again? That diagram.
Yeah, sure. The input get is determining what information should I take from the um, current time step, that xt.
Yeah. Yeah. And that gets stored into the state.
Yeah, so it is um, it is getting added to the cell state by this connection.
Also, what type of input would the forget gate hide, or forget?
W- What type
What's
of like what exactly is it looking for? That's
yeah,
something
yeah, yeah.
that that would we would not know, but the general or the rough idea is it is um, it is kind of filtering whatever is coming from the previous time steps. It is kind of filtering what is required, what is more significant in order to use, that would be used in order to generate an output, a correct output, and what would be not so significant. But what exactly is it looking for? That's something that is up to the model. Like it is whatever it is would be helpful
Okay,
for it.
that makes sense.
Yeah. That's very interesting. So the main change in the LSTM is, or one main change is, it looks at the new input item and it uses that to determine what things can be erased from the memory.
Yeah. So they're just like in the simple RNN, it was taking into account the immediate connectivity, like the short-term dependency between
Yeah.
different time steps. But the problem was, the longer the context becomes, the more difficult it was for it to determine or to remember what was occurring earlier in the sequence. So this long-term cell state is kind of navigating across all the different time steps in order to also solve the long-term memory problem. But still, I mean, it was aimed at mitigating the problem of vanishing gradient or remembering long-term context information. Still, it was not able to solve that issue. The problem is, the bigger the input becomes, the more difficult it becomes for this LSTM to be trained. Because remember, LSTM processes every single time steps one at a time. So you cannot make use of that parallelization, which is what we do in CNNs or in transformers.
Yeah.
You cannot easily do that in LSTMs. So even though it mitigated up to some extent that context problem, but the bigger it becomes, um, or the more cells you add to it, the more difficult it becomes for this network to be trained.
A lot of people said that you should study or teach LSTMs before transformers, and now I can really see why that is. There's some aspect of the forget gate that kind of reminds me of the keys and values aspect of the attention in the transformer a little bit.
Yeah, the key difference between an LSTM and transformer, although the target of both of them is the same, to remember long-term context, um, but the difference is, transformer, as you have seen, is taking into the is processing all the inputs at once. So like that parallelization operation becomes possible in transformer architectures.
Yeah.
So the transformer is not processing every single time step one at a time. It is rather processing it um, across all the different steps at the same time. So parallelization becomes easier, and with that, you can make it bigger and bigger in order to, like, theoretically that context window could be infinite if you have infinite compute power. Training it is easier because of the parallelization and because of its internal working. For LSTM, it is difficult because it is processing sequentially every single time step. uh, but yeah, there are like some or very little similarities between what an LSTM is doing and what a transformer is doing, although the goal of both of them is the same. Internal working of them is drastically different.
Hmm. Okay.
So I think with that we can move towards coding.
Yeah, I think that's plenty of theory. Um,
Yeah.
Now, for the coding example, we're going to use the LSTM. Now, just one question. So in our example that we're going to show, um, we actually pass multiple inputs into the LSTM at once. Now, is that the same thing as, like, for example, we have time series data, and then we're passing in like seven inputs to get one output? Is that basically what you just showed? Seven seven occurrences of the neural net.
Exactly.
Okay.
So that TX that I was talking about is 7 in this case.
Okay. That that makes a lot of sense. So we had this idea, or Naveed had this idea, and we have Felix and Victor here with us now.
Mhm.
That we could train a model. Hey Felix, how you doing?
Good.
Good to see you, man. So um, we had this idea that we could train an RNN, or Naveed did, in order to predict the price of Bitcoin and get rich. So the model actually worked very well, although unfortunately we cannot use this this model to get rich, and you'll see why. But so this is the main project. Victor, I'll just put you on mute because you have a bit of background noise, but unmute yourself if you have a question. And this is the notebook. So I trained this LSTM on historical Bitcoin data. So let's see. Yeah. So the data that I used for this is I've put it into my Google Drive because it was so much data, and I've sort of trimmed it down in order to train this network. But maybe I can just have a look at, maybe I can just find that original data set here on Kaggle. So it's just called Bitcoin historical data. So basically it is the daily, actually in this data set it was by minute, but I've changed it in my code to be by day. And it's just like the daily price from 2012 to 2021. So obviously there's a lot of huge fluctuations and small fluctuations in that time. So yeah, so I just downloaded it here from my Google Drive, and this is a public file, so you can run this notebook as well, and it should work. Looking at the data, there was all of this missing rows, which is annoying. So I just took out the closing price and the timestamp, and I just took one per day. Oh yeah, there should really be one closing price per day anyways. And then yeah, I just put that into a simpler data frame that looks like this, where it's just a day. So if we visualize that, we see here the wild ride of Bitcoin price over time. Now, in order to train the model and to test it, of course, we cannot anymore just randomly choose 80% of this. So what we did is we took the first 95% to train the model, and we're going to test it on the remaining 5%. So the last 5%. So that's what the train test split is here. Now, for this training section, actually, I think Naveed understands better how this part works, but so I'll let him add to what I'm saying. But basically, we want to train the model on 7 sequential items at a time in order to predict the next one. So basically, given the Bitcoin price of every day in the past week, predict what is going to be the price of Bitcoin tomorrow. What else? Yeah, what am I missing here, Naveed? What else would you explain?
This is literally all that's happening. So because we have sequential data coming for previous days, we cannot take all of it at once and feed it to the network. So we have to segment it into smaller chunks.
Yeah.
This is exactly what I meant by context window. So you have to fix a certain context window where the network looks back through those values and then predict the next value. Here, the context window is 7, but you can literally play with it because this is a hyperparameter. You can increase it, you can decrease it. The longer you make it, the difficult it would be for an LSTM model to remember what was occurring in the initial values. The shorter it is, the difficult it is for the network to determine what's the next value, because it is not having lots of information of what's occurring before that. So you have to select somehow a sweet spot between too long and too short in order to predict the next value. And the code is just simply taking the entire values, and using the dot window method, it is segmenting those into uh, the lengths set by the window, and then the rest is just batching the data and kind of creating that x and y, uh, the x which is the features, and the y which is the label. So if you, let's say, have 8 values, first 7 goes into the features, the 8th one goes into the target or the
Yeah.
y, and then the next, you just simply drop one from the beginning and add one to it, and that becomes the next features, and then the target is the next value, and that's how you construct this entire data set. Here the code that is presented here makes use of the internal TensorFlow datasets package, but you can literally construct this using any other way. Like you can construct it using NumPy, where you have x and y, x representing the previous windows, previous
Yeah.
values, and y representing the next value.
But so we're also not just training it from the beginning to the end. There's like a shuffling going on here, right? So it's randomly training it on windows of 7 throughout the data set. Is that on well, throughout the time series? Is that right?
Exactly. So this buffer of 1000 just simply means that because we have now segmented the entire data into these 7 length windows, uh, we will have lots of different windows there. And this buffer just simply picks thousands values at random because it
Okay.
does not want to store all of it at once, or store all of it at once into the RAM. It creates this buffer, which then is easier for the computer to efficiently manage the data.
Okay. So the main thing to get here is that we're taking periods of 7 days along with the next day after that, and then using a bunch of those at a time, randomly chosen throughout the time series to train the model.
Yeah, James, if you allow me, I can quickly explain that using the whiteboard.
Oh, yeah. What? Sure.
This window operation, maybe it would make more sense.
Sure.
So let's say we have these values 1, 3, 9, 8, 7, 4, 2, 1, and my window length is 7. How am I going to present this? Like, suppose I'm interested in predicting what is this, what values would be coming next in this sequence. So let's say this is the 5% data that you have set aside, um, that you'll be testing your model in order to predict those values. So what we do is, if the context window is 7, we just simply take 1, 2, 3, 4, 5, 6, and 7 values. We store them in X, and this one becomes the target Y. And this constitutes one example, one training example. Now, to form the second training example, I just simply then take these. So starting from here and going up to here. Now this becomes the X of the second, and this becomes the Y of the second example. So this is X2, Y2, let's say. That was X1, Y1, and so on. We just simply then keep dropping the previous value and keep adding the next value in the sequence. So then this becomes the next, which is X3, and then that would be our Y3, and so on. That's how we generate our X and Y. Now, once I train my model using this X and Y, how can I then make use of this model to do prediction? Well, I just simply take the previous 7 values, which for this case would be, let's say, this one, and till this point. And making use of these values, my model would be then able to predict what is coming here. That would be the prediction or the target of the model. And this example that James is presenting is what is called open loop forecasting. So these previous 7 values that he's using, these come from the correct data or from the true values. And this the model is only predicting one future value at a time. But there's also a second variant of it, which is called closed loop forecasting, where you can just simply then keep appending whatever the model is predicting to the previous window, and then the model will be predicting the next window. So you can then make predictions on top of predictions. Although the more you go into the future in such a model, the lesser your confidence becomes of how correct the prediction is. But you can also do something like that as well.
Yeah,
I hope it's clear.
and we'll come back to that in 1 minute, the open and closed loop stuff. So here we go. So moving on to it's my little bird. Moving on to the model itself, we have, as you can see, window has been defined to be 7. So the input here has 7, and then we have an output with 1 because we're predicting 1 value, and we have a LSTM layer, and this is the number of this is the number of nodes.
LSTM cells.
LSTM. LSTM cells.
Yeah.
And then we followed that with a dense layer.
Yeah, so the LSTM cells are the ones which would make use of those hidden states that I was talking about. And we are making use of 64 of them. So all the explanation that I was presenting was just for one cell. You can literally take any number of them, and then every single cell might be looking for some different patterns that it could be seeing in the data. Usually for LST models, because they are they're heavy, you don't add lots of LSTM layers. Usually one layer is enough with a decent number of neurons. Here it is 64, and then you can then follow it with a dense layer, but you can also skip the dense layer. That's totally an option.
Okay, let's get to the fun part. So I trained this with 10 epochs. It did not take too long, maybe like a minute or two. And then this is how the training came out. So the loss started at all the way up here at 100,000 and down to 31. So this runs the forecast. As Naveed was saying, this is a open loop model, which means it's always going to predict the next day based on the last 7 actual days of data. It's never going to use its own prediction for tomorrow to predict the day after tomorrow. You could make a closed loop model that does that. It would be much less accurate, of course, but it would allow you to predict further into the future. So we're just using the open loop. And this code here combines the true price data we have with the predicted price, and there's just a little bit of math we have to do here, as the number of values we end up predicting, just because of the size of the window, the number of values that we end up predicting ends up being a little bit more than the values we have in the actual data set. So that just ends up being 6 more. So we just adjust that. And then here we have like the final data set with the true and then the true and the actual predicted price. So let's actually see how that looks. Okay, here it's all overlaid. As I mentioned, so when I first saw this, of course, it's like, wow, like it's really, really similar. But just remember that every day is predicted based off of the last actual week. If we would make this into a closed loop model, you should really expect, obviously, that it's going to go all over the place. It's not going to follow the actual the actual chart, because there's not enough information here in the past to predict all of this that's going on after that. So let's look a little bit closer into this. So this is like, as you can see here, as you can see, for predicting like the next value based off of the past chunk, it's doing pretty good. Like oftentimes it goes down when it should go down, and it goes up when it should go up. So that's, and then here's like even more zoomed in. It's like, for example, here, the next step would have been to go down, and it did go down, but not to the same extent. So it's generally learned some trends having to do with, I guess, volatility in the Bitcoin market, which is interesting. And we can measure the error. Measuring the mean squared error or the mean absolute error is going to give a really high number because we're dealing with thousands of dollars. The mean absolute percentage error here shows actually, okay, so this should be 19%. Wait, no, that should be 1.9%, which is actually super low. Isn't that, Naveed?
Yeah. So the value is low. The mean absolute percentage error usually divides the error by the maximum value. So it normalizes it. That's why the values are low. But as you can see visually, it is not that much accurate as this map value is kind of presenting.
So yeah, actually I have some more thoughts on this, but yeah, I'd like to just, since we're running close to the end, just like to ask for all of your thoughts and questions that you have on this.
Yeah, right. So you mentioned that this is an open loop model, so you can predict like basically what you said is one day into the future.
Yeah.
By considering the last few days. So when you have this curve here, this is more than just a few days, right? So it's basically considering the actual data of all of these, like the rolling, kind of 7 days prior to predict the next day, right? Is that correct?
Exactly. That's right. That's correct.
So what that means is, with this accuracy, you could actually, if you would input like the live data from the last weeks, you could predict tomorrow with a, I don't know, 2% average error rate.
Yeah. So the, yeah, I don't know about the 2% error rate, but we could test that. We could calculate that, what the error rate would be, and I guess that would depend on exactly how you'd measure error, like how close you'd want it to be. But that actually, so one of my thoughts was, it would be really interesting to see what percentage of the time it gets, it knows if the price went up or down. I think that would be really interesting.
Right, because that's actually all you need, right? If you want to bet on it. Yeah. It doesn't matter how much it goes up or down. It just matters if it goes up or down.
So
basically.
I would, so I want to add another
Yeah.
metric to my notebook, which says exactly that. What's the accuracy if I just want to know if it went up or down? And if it's better than 50%, if it's better than 50%, then it's very interesting.
Then it's better to use that than not to use it.
Yeah.
Whatever that means. Yeah.
Yeah. So if anyone wants to work on this project with me later, who knows? Maybe we'll become millionaires.
Yeah, sure.
Great.
This model is actually just trained for 10 epochs. So if you go to the learning curve of it, the loss was sharply going down. If you would have trained it for, let's say, 100 epochs, this model would have been even more accurate.
True.
So as you can see, the loss is still going sharply down. The 10 epochs is definitely not like it has stopped training early.
Right. Super interesting.
Yeah. Maybe we should found a crypto startup.
A DAO.
Right.
So
Sweet.
yeah, so for you all, of course, we have one more session this after this one on Thursday, and this isn't too difficult to um, reproduce. You have the code here, and then I've given some other data, stock market data, weather data. The only thing that matters is that the data is sequential data. So really, anything that is sequential in time would be interesting to see, and should be pretty easy to fit to this. The most annoying thing here was probably just like the time, like getting the right code to format everything correctly, like to date time. Everything has to be formatted as a date time. That's all.
Yeah,
Right.
that's often the common struggle. But you can completely ignore the date from all the code and just simply work with the values themselves.
Right.
But the problem is then you would not know when which value occurs when. So in order to keep a track of that, you would need to have this timing or date and time information properly formatted.
Yeah. So in other words, we think of it as values on dates. The model just thinks of it as values in an array.
Exactly.
And so there's a little bit of juggling that has to happen to put the dates back on after the prediction has happened. But that's all.
Exactly.
What do you think, Victor? I've muted you.
I'm sorry about that. I didn't quite get it. My data was a bit choppy at the time. Can you come again?
I just asking. No, it's just asking what you think about the project in general.
Yeah, it was really lovely. I didn't expect it to be that accurate. Like it was very, very, very close to the
Me
actual
neither.
results. It's just amazing.
I guess we'll see. Cool. Victor, by the way, this is you. You guys haven't really met before, have you?
Not really, I think. No.
Victor's from the original test course that we did, and he's done all the same lessons.
Oh, there was another course before that?
We had a very small group testing the lessons before you guys did.
Oh, okay.
You guys done all of the same 5 weeks as well. He and
Cool.
Burhan have both done them. Yeah.
Sorry? What was the last thing you said?
Victor and Burhan together.
Victor and Burhan. Okay. Hi, Victor. Nice to meet you.
Yeah. Hello, Felix. Nice to meet you.
Did you have to get up early as well, or where
No.
are you based?
No, it's around afternoon.
Okay, that's better.
Yeah. Pretty much the same as Europe. So cool.
Yeah. Thanks so much.
yeah, thanks, guys. And see you again on Thursday, and we will go over whatever models that you come up with, and we'll test the results.
Thanks, James.
All right. See ya. Bye.
Bye.